Hey everyone, and welcome. Today, we're going to jump into one of the most elegant and honestly powerful tools in all of machine learning, the Support Vector Machine, or SVM for short. We're going to break down exactly how this thing works to find that one perfect dividing line in a whole sea of data.
So let's start with a puzzle. Imagine you've got two groups of, well, anything. Dots on a graph, emails categorized as spam or not spam, you name it. The big question we're tackling today is this. How can a machine look at all that data and draw not just any line to separate the two groups, but the absolute best possible line?
Okay, to get our heads around this, we're going to start with a really simple, almost perfect scenario. Picture this. You have two clouds of data points, and they are cleanly, perfectly separable. What that means is you can take a ruler and just draw a straight line right between them with no blue dots on the red side and no red dots on the blue side. Easy, right?
Now that dividing line has a bit of a fancy technical name, a hyperplane. But don't let that word scare you. Seriously, if you're looking at a flat, two-dimensional graph, a hyperplane is literally just a line. If you're working in 3 dimensions, it's a flat plane. It's just the official term for our divider. That's all it is.
But here's where things get really interesting. Even with our simple, clean data, you could draw tons of different lines that separate the two groups, right? You could tilt it a little, shift it up or down, and they'd all technically work. So how on earth does the machine choose? Which one of these infinite possible lines is the optimal one?
The answer to that is the first big, brilliant idea behind SVMs. It's called the maximal margin classifier. The idea is that the best line isn't just any line that separates the groups. No, the best line is the one that creates the widest possible street or buffer zone between the two sides. It pushes as far away as it can from the closest points in each group.
So why do we want the widest street possible? Well, it's all about building a more confident and robust model. Think about it. A wider margin means if a new data point shows up near the boundary, we're much less likely to get it wrong. And this brings us to a super important term. The actual data points that are right on the edge of that street, the ones defining how wide it can be, those are called support vectors. They're the critical points that literally support the entire boundary.
Now that all sounds great when the data is perfect. But let's be real, real-world data is almost never that clean. It's messy. So what happens when the groups overlap a little bit? What do you do when you just can't draw a perfect straight line without getting a few points on the wrong side? Our super strict, widest street approach would just fail.
And this is where we need to get a little more clever. We introduced something called the soft margin classifier. You see, unlike that rigid all-or-nothing approach, the soft margin classifier is flexible, it's forgiving. It's willing to say, you know what, I'll let a few points be misclassified if it means I can create a boundary that has a really good margin and works better for most of the data. It's a trade-off, really, between perfection and being practical.
And how do we control this flexibility? We use a little tuning knob called the cost parameter, which you'll almost always see written as the letter C. This parameter is basically how we tell the model what the penalty, or the cost, is for getting a data point wrong.
Let me break that down. If you set a low cost value, a low C, you're basically telling the model, hey, I really prioritize a nice wide street. I'm okay if a few points end up on the wrong side of that street if it gives me a more stable boundary overall. But if you crank C up to a high value, you're saying, I hate errors. I want you to avoid misclassifications at all costs. Make the street as narrow as you have to, just try to get every single point right. So that C value is how we fine-tune that balance. Okay, we've handled clean data. We've handled messy, overlapping data. But now we come to the toughest puzzle of all. What if your data is arranged in a weird shape, like a circle or a spiral? What if there's no straight line in the universe that could ever be a good separator? This brings us to the most powerful and, frankly, almost magical part of support vector machines. It's called the Kernel Trick. At its heart, it's a super clever mathematical shortcut that lets the SVM find these complex, curvy, nonlinear boundaries. It works by projecting the data into a higher dimension where, suddenly, a simple flat divider can separate it. And the best part, the trick, is that it does all this without actually having to do the heavy, expensive calculations of moving into that higher dimension. Here's a great way to picture this. Imagine you have a bunch of red and blue marbles mixed together on a flat table. You can't draw a line to separate them. The Kernel Trick is kind of like hitting the table hard from underneath. For a split second, all the marbles fly up into the air. And from a side-on view while they're in the air, you could totally slide a flat sheet of paper between the red and blue marbles. That's what the Kernel Trick is doing, just with math.
Now, in practice, we use different kernels to pull this off. The two you'll run into most often are the polynomial kernel, which is great for creating smooth, curved boundaries, and it's controlled by its degree. And then there's the radial, or RBF kernel. This one is incredibly flexible, and it's controlled by a parameter called gamma. Honestly, RBF is often the default choice you start with because it works so well in so many different situations.
All right, enough theory. Let's see how this actually works on a real problem. We're going to look at the heart dataset. It's a classic dataset used to try and predict whether a patient has heart disease based on a bunch of different medical readings. This is exactly the kind of messy, high-dimensional problem where an SVM can really show what it's made of.
Before you go off and use SVMs on your own projects, there are a few practical rules of the road you absolutely need to know. First, always scale your features. You need all your variables on a level playing field. Second, you have to tune your parameters. Finding the right C and gamma is absolutely critical for getting good results. Third, just be aware, SVMs can get pretty slow on really huge datasets. And finally, even though they're designed for two-class problems, they have some clever built-in strategies to handle cases where you have 3 or more classes to predict.
So, let's sum it all up. What makes SVMs so powerful? Well, first, it's their unique focus on only the most difficult, most informative points, those support vectors. Second, that core concept of maximizing the margin creates an incredibly robust and stable boundary. And finally, the kernel trick gives them this amazing ability to solve ridiculously complex nonlinear problems in a really elegant way.
And that brings us to one last thought to leave you with. The entire philosophy of the SVM is about finding the best solution by focusing on the hardest cases, right on the boundary. That's not just a machine learning idea. It makes you wonder, in other parts of life, in problem solving, in design, where else could we find better, more robust solutions by focusing not on the easy stuff in the middle, but on the challenging boundaries? Thanks for joining me for this explainer.